Okay, so yeah, I'm here to talk to you about developing human-to-robot trust. I'm also part of the project that Dr. Davidson was talking about earlier, in part because my overall research program as an associate professor at Oregon State University has to do with kind of haptics, assistive robotics, embodiment, largely thinking about many different types of human-robot interaction and kind of tactile sensing as it pertains to robotics. So that's what my lab is all about. But in the past, I worked at Procter & Gamble, I worked at Microsoft Research, and I kind of became passionate throughout the process of working in industry, studying in academia, and now working as a professor about solving difficult basic science problems and then ideally translating the outcomes. So it's exciting to be here talking to all of you, and hopefully we could get some of that going surrounding this idea of human-robot trust through the current work or future work surrounding this topic. This project was a collaboration with another faculty member, Hussam Abbas at Oregon State. He's over in electrical engineering and computer science, thinking about formal logic, robot ethics, even autonomous robotic racing. So kind of a wide breadth of skills coming together under the umbrella of this project. Since there are lots of fundamental technical challenges that we have to solve even before we get to the idea of evaluating psychologically how people feel about systems, how we can get them to use these amazing technologies that we've been hearing about throughout today and yesterday that we want them to use, but maybe that there's some unease to adopting. So those are some of the key ideas here. A few students, Naomi and Jinhan, from mine and Hussam's labs were involved in this work as well. And of course, I want to acknowledge the industry partnership and sponsorship. These three partners were sponsors of the rounds of the funding that have contributed to this work so far. In particular, we talked to Boeing some as we were forming this project. We talked to Cobot team. We wanted some user-inspired problems that drove at least parts of the work in this space that I'll be presenting today. And we're actually looking to do a little more user-inspired research design in the future too. So if any of this resonates with you and you can think of problems where you have, especially robotic technology, but perhaps other types of technology too, it's amazing, the potential is great, but the people don't want to adopt it or they're trusting it too much. That's kind of the core problem, core idea related to what I'll talk about here today. So yeah, thanks for the past support and looking forward to conversations related to that with many of you throughout the day. As far as the current project scope goes, basically here, we're thinking about human-robot teaming. That's the core context of this work. As robots appear in industrial contexts, especially without cages, which is kind of the historic model of robots in industry, we've had them for quite a while, but they're usually isolated from people in industrial workspaces. So as cages are disappearing, as we have more direct human-robot interaction in industrial contexts, there's a need for better human-robot communication, rapport building, trust as well. So that's sort of key to the central idea of this project. Overtrust and failure to adopt, I think, are very common. I don't know if it's too high stakes, but I was thinking of even doing a quick straw poll, off the top of your head. Can you think about maybe in your organization something that went wrong because people were trusting tools too much? Maybe high stakes among your some people hand races. What about failure to adopt? Maybe you brought forward an amazing new product or technology. The people in your organizations just didn't want to use it. We can talk later in smaller groups too, but at least a few brave volunteers can think of examples under both of these umbrellas. So that's sort of the core context of why I wanted to pursue this work. There's a lot of great technology out there. Sometimes it has shortfalls even if it is amazing, and we want people to be able to understand better what these shortcomings are and work around them and use collaborative contexts. And we also see examples where we have this amazing tool, and for whatever reason, the people who are supposed to be using it just don't ever adopt it. So this is really fascinating to me and seems like an important part of the overall enabling technology process. We want to drive this amazing change, and we want it to, in the end of the day, be impactful, successful, safe, actually used by our organizations. And we suspect that when we're doing this for robotics in particular, that we may need multimodal communication. So most likely you have alerts, you have lights, you have sounds, you have on-screen messages in your own organizations already when it comes to automated technology interacting with people. So when we're thinking about robotics in these spaces and we're wanting to maybe grab human counterparts' attention as they interact with robotic systems, we're thinking about a suite of potential communication mechanisms, partly because the space is already so noisy and crowded. Maybe we need motion, maybe we need sound, maybe we need verbal speech, that kind of thing. Although under the umbrella of the project I'll talk about today, we're mostly thinking about expressive motion as a way to augment the human-robot successful teaming in industrial contexts. At a broader level, the framing of this work has to do with collaborative robotic systems, which for about a decade have been an exciting idea. We've seen many bids in industry to develop collaborative robotic arms. Some of these platforms are still in use, some are now defunct, but you can kind of see the progress, driving change in the model of robotic systems, moving from robots isolated by cages to robots that can move around warehouses with people, directly physically interact with people, that kind of thing. And two platforms in particular that I've used throughout my work so far are the Canova Gen 3 arm and the Hello Robot arm. The Canova is nice because it's a collaborative robotic system in a classic industrial robotic form factor. Robot arms, they've been around for a long time, although historically more often in cages than not. And then the Hello Robot is nice because it represents a modern mobile manipulator. So a robot with a mobile base and also a grasping arm, which when you want to deploy robots and really get impact out of them, it's helpful if they can grasp things and move around floors with things. So we were thinking about those robots as we developed this work. In the current phase of this work, we continue working on the project this year. We're thinking about the Canova arm more. And in the work I'll present here today, we were mostly thinking about the Hello Robot stretch, so the mobile manipulator form, which can move around and also manipulate objects for things like part tending, pick-and-place operations, warehouse operations, that sort of thing. And when we boil down the problem to kind of its core context, the basic problem we were trying to address, again, is that communication between humans and robots is limited. Most industrial robots, at least for now, lack these nuanced multimodal communication modes, which can be detrimental when it comes to adopting and safely using new technologies, especially robotic technologies in industrial spaces, collaborative robots. So our goal was to advance the state of human-robot teaming by improving robot nonverbal expression, seeing if we could fill in some of these gaps and understanding what's the system status, what's the system need, intentions, and being able to more successfully symbiotically work with these types of systems in industrial contexts. For the scope of this round of the work, this first year of the project, which is kind of the core of what I'm presenting here today, I'll look forward to presenting at the end of this project here the latest updates with the Canova Gen 3 as well. But for now, we were really focused on the solution of communicating robot intentions and internal states through expressive motions. In my lab's work in the past, we also have sound-based communication, both verbal and nonverbal. We've thought about things like the physical form of the robot, how the way the robot looks actually influences the way people approach it, adopt it, etc. So for this project, we wanted to fill in one of the remaining slots in kind of the potential multimodal human-robot communication, thinking specifically about motion. But when you zoom out and think about the broader scope of my lab's research, this gives us just one tool in a suite of tools to be able to elicit successful kind of human-robot symbiosis in industrial contexts. So backing up to the core research questions, here within the scope of the core work I'll present today, we wondered how motion-based nonverbal expression of the robot could communicate its intentions and states to nearby people. So you'll see that in some robot videos that I'll show, a beginning kind of psychological experiment that we did with robots and people, and I'll talk at the end about how we can kind of expand this, thinking about broader multimodal human-robot communication and the work we're doing this past year. But basically, robots have internal states, they have intentions, they might have a status like low battery, maybe even from the last presentation, a tool is about to run out and you need to replace it. All kinds of automated systems. So understanding things about system state, whether it's notification, warning, or like higher urgency error or alert, This can be really helpful to be able to convey in a broader range of ways. Also understanding things about intentions, especially when it comes to mobile manipulators. If you're walking around a warehouse with a robot or autonomous forklift, you might have done this before, understanding where the system is about to go, where it's planning to go next. Even simple things like that can be quite challenging. So we're thinking about those types of problems, helping robots to communicate states and intentions for more successful co-location by humans and robots in industrial settings. This is important, I think, because being able to do this well can help with those challenges of overtrust and undertrust that I talked about earlier. So under the umbrella of the work I'll talk about today, there were kind of three main challenges or research tasks that we dug into. One was simply representing key robot states. So I talked about hypothetical things that we might want to communicate, but within the context of the work I'm presenting, what did we focus on? We started more in the realm of thinking of notifications, warnings, and then errors, thinking about what would be really critical to potential use cases and industrial partners' work that we were collaborating with for the project. We thought about communicating key robot states then, so if we want to know, if we already know what we want the robot to notify nearby people of, then we can think about how to communicate that. And then finally an assessment where we brought people in, we showed their robot behaviors, these nonverbal robot expressive motions, and tried to understand whether behaviors were perceived as intended. So this first part kind of dealt with looking deep into the error logs, looking deep into the system architecture of this particular robot. This is a process you can repeat for other robotic systems too, but just trying to understand, like for this system in particular, what would we want to communicate to people when it comes to notification, warning, error. So we looked at sort of logs that the robot already had baked into its system. We looked at the architecture, thinking about things like, is this wired or wireless? Does it have battery on board? What parts of the overall robot could be functioning correctly or not functioning? We aggregated all of this information into kind of a large table spreadsheet, thinking about whether each of these error states or potential notification states were urgent, if they urgently required attention, if they're just helpful information to communicate to nearby people, or maybe even if they're just simple notifications. Like it could be helpful for nearby people to know about this, but it's not kind of urgent or imminent. You don't necessarily need to grab their attention and force them to know this if they're just passing by and might not need to know it. We also thought about kind of state machines. So for the Hello robot, robot that I showed before, the Stretch RE2, we were using it for pick-and-place operations in our first topic of study. So we thought about how this bakes into kind of an overall finite state machine. This is important in part because at different parts of the state machine, different parts of the robot are active. So you could imagine that a warning about a gripper is more ultra-urgent when the robot's about to do a grasping task compared to when it's just driving across the room to approach a target of interest. So moving right along for now, we can dig in and talk about some of these topics as interest all of you later as well. But we next thought about how to communicate these key robot states. So, in the process of grasping, you could have things like localization failure, an arm isn't working properly, a low battery state, since this is a robot that's moving around, operated off of a battery, that kind of thing. And we use the overall framework again of thinking mainly about notification, warning, and then more urgent alerts. So we thought this would be sort of most relevant to everyone's bottom line here, most relevant to early introduction in industrial contexts. We were thinking about this as it pertained to a mobile manipulator that was performing a pick-and-place grasping task, which can be relevant to all kinds of things, part tending, warehouse settings, other pick-and-place. When we were thinking about early expressive motion context with that overall notification, warning, error framework in mind, and the grasping context as well, we thought these might be some representative early examples that we want to be able to demonstrate through simply the motion of the robot to nearby people. So we thought, maybe just conveying the status of the robot, I'm on this pick-and-place mission. That's a notification, but it's not urgent. Other things like projecting where the robot's about to go, warning about something like low battery. or even letting the user know about more urgent problems like localization failure, sensor failure. This was sort of our early structure motion context for this system. And then we wanted to design robot motion that would communicate each of these. So in each of the videos that are already playing up here, as you look through them, you hopefully see robot motion that could potentially convey these important messages to nearby people somewhat naturally, hopefully even without a need for training, which I know in industrial settings is expensive. We want the messaging of the robot to be so simple, so straightforward that people can just look at these things and understand what the robot's trying to convey. So as we design these behaviors, we thought about kind of how expert movers and dancers might address this problem. In localization failure, the robot's kind of rotating, looking around is one example. Low battery, the robot's getting lethargic and the arm of the robot is falling. So hopefully starting to convey some of these ideas about important robot status that might need to be known by nearby people to the robot for successful adoption and symbiotic use of this type of system in industrial contexts. We didn't want to just design the motions and say, we did it, they're great. We also wanted to evaluate them, so we ended up with a set of these early motion contexts, basically two that were more of a baseline, nice to know information but not urgent information contexts, like picking places going as expected, some that conveyed partly functional statuses, low battery, you need to plug the robot in or help the robot get to a charging dock soon, or something like the uncalibrated tool, which in some cases might be urgent. I'm about to grasp that it's urgent. In other cases, maybe the robot's just moving across the warehouse floor for now. It could get to its dock and be serviced later. And also thinking about more urgent cases where the robot would be non-functional due to the status message. So cases where we really want the nearby person to notice something is wrong and act right away. So those were our early concepts, and then we wanted to, again, assess these concepts. So we used a small in-lab human subject study to begin to assess whether these robot motions were conveying the types of messaging that we wanted. In this early pilot experiment, we engaged with 8 participants, brought human participants into the lab. There was the mock context of the stretch tending parts, so it was doing a pick-and-place operation of a block, moving blocks from one table to another in the lab space. And we measured things about the behavior of the people who were interacting with the robot. So like when they noticed there was an error, whether they interjected and said there was an error happening. And also some self-reports, so like survey-based methods on these scales from strongly disagree to strongly agree. How much do you think these things are happening? As well as recording demographics of our participant group. The outcomes from the first round of robot motion concepts conveyed that folks had a good understanding of the baseline cases that didn't require intervention. They could kind of tell that the robot was successfully performing its task, didn't notice anything urgent that needed intervention. They also understood well the low battery and localization failure tasks, or behaviors of the robot, nonverbal communication from the robot that was supposed to convey that these things are happening. There were other motions that, at least in this first round of work, weren't fully developed. Folks had difficulty interpreting the uncalibrated tool and disconnected tool context. And we did see overall that self-reports, so those survey-based input from folks about urgency, difficulty to ignore, and perceptions of an error being present trended in the direction that we wanted. So as we formulated those different hypothetical robot statuses, we wanted some to appear more urgent than others, call for intervention more urgently than others. And we did see, as far as kind of descriptive statistics went, that everything trended in the direction that we would have wanted across those groups. So some potential for improvement, but some promise, especially in proof of concept of certain nonverbal motion-based robot messaging. In the current times, we're pushing this concept on to the next phase. In the current work, we're looking more at robot arms, in part because I think these arms give us a little fewer more degrees of freedom to be able to convey expressive motion in a variety of ways, sometimes with kind of kinematic redundancies that help us. get a little more creative. So we're working now on the Canova Gen 3 with a similar idea, trying to convey different types of expressive motion naturally with the robot arm to add to our overall cadre of nonverbal and verbal robot communication methods that can contribute to the overall multimodal communication of industrial robots to nearby people for more successful collaboration and teaming. So right now we're working on conveying those expressive motion ideas to this arm and doing kind of a second round of evaluation. I'll show you some of the motion contexts, partly because robot videos are fun to see, but you can see with this robot arm, even if the functional task of the arm is the same, in this case, the robot's kind of trying to approach a particular point of interest as if you're beginning a pick-and-place task, approaching the object of interest to begin with. You can do it in a more direct way, you can do it in a more indirect way, even if in the end you're approaching the same destination. So this could be useful as one example for conveying whether the robot has sensor information that's very good, it feels very confident about its directive, or if it is less certain, maybe a higher degree of uncertainty coming out from its onboard machine learning classifiers as one example. Here's one other style, a free style, where in the end the robot is still approaching the same point of interest, but in a very different way. We explored several axes of expressive space as we were starting to put together this project. For now, research outcomes and applications of this work, I've alluded to this somewhat throughout, but especially with the robot arms that we're currently working with, and to some extent with the mobile manipulators, like the Hello Robot stretch robot. Because of kinematic redundancies, it's possible to be doing some functional core tasks, like the pick and place, part tending, those types of interactions that I've been talking about throughout the presentation, while also layering on some more informational motion. So it doesn't get in the way of what the robot is already doing, but it can illustrate some other type of quality, some internal state, some intention of the robot, just based on that motion layering. So the example I just mentioned of the direct versus indirect approach of the robot to some point of interest is, a direct motion might naturally convey confidence, whereas the indirect motion might convey more uncertainty or something wrong during a motion. So overall, we're curious about this potential of expressive motion to convey status information very naturally to nearby people in these collaborative robotic system contexts. Resulting capabilities, I've touched on this some throughout too, but we think being able to render expressive motion and apply it can help convey things about robot status and intention, all the way from very functional safety warnings in industrial contexts, all the way to the social, if you have this type of robot in your home setting, in personal day-to-day use, or even in campus delivery, if you've seen those on-campus food delivery robots at Oregon State or elsewhere. It's helpful for robots to be able to convey things about internal state and intention so that nearby people can stay safe, move confidently, have a good experience as they're interacting with these systems. We're thinking in general about presenting multimodal information from robots to be able to support this goal of more successful human-robot teaming. So in our case, within this presentation, I talk mostly about expressive motion, but my lab also thinks about, again, sound and form, all kinds of aspects of, as people approach these types of robotic systems, what they will presume, what they'll naturally infer from the way the robot looks and sounds and moves. And I think it's especially relevant in collaborative robotic systems, so as robots are leaving cages in a broad range of settings, from industrial to even day-to-day interaction on the street or on sidewalks. We need to think about this type of topic in order for people that overall have good outcomes, good experiences, safe interactions, and efficient interactions with robotic systems in day-to-day use. So for next steps, we're curious about integrating, again, many of those different multimodal communication methods. We're also curious, especially based on conversations throughout this project cycle, about things like robotic pallets and carts in industrial contexts. At least as I talk to folks in industry, I've had some window into Amazon's operations with a Proteus robot. There are also examples like the Carter robot, so a robotic pallet a robotic cart that's meant to more naturally interact with people, be much less annoying for people to use in warehouse-based picking operations. We're curious about the potential added benefit of all of this multimodal communication in these robotic industrial contexts that, especially over time, are more and more relevant, more and more in demand. Online commerce is at an all-time high. These are really important questions that we'll need to be able to answer to efficiently serve the consumer and also have good interactions between humans and robots in a broad range of industrial warehouse settings. So that's one case that we're curious about in the future that I'd be especially interested to hear about if folks in the group today have past experience or future interest. And we're also excited about testing in case study type contexts. So for the evaluation I presented about today, we stayed in the lab, but really leaving the lab, trying out these ideas in industrial context can be much more impactful and exciting. So again, following this path of having worked in industry and academia, I'm excited especially about translational work that can come and impact all of your day-to-day applications in beneficial ways. So I'm excited about that too. In proposed future work that I'm hoping to undertake related to this project, I'm planning to do interviews with industrial partners, learn about applications similar to the ones that I've been talking about that all of you are already excited about, and hopefully pick a few where we could deploy a test robotic system. I've seen this work well as one quick example with interns who come from our robotics program and work with folks over the summer, and maybe be able to serve part of your bottom line needs while also being able to conduct research to evaluate that this type of interaction can be beneficial. So that's all for now. Thanks for listening, and happy to answer any questions you have.